Hi everyone. We're going to start our next session. Welcome back. This is the Games, Entertainment, and Other Applications segment. May I please invite Professor Leong, the chair of the session, to say a few introductory words, please.
Well, thank you, Tara. Good afternoon, everyone. Welcome back to the sessions on applications of cognitive neuroscience. So before I start the session proper, I thought I would like to congratulate Tara and her team of students once again for putting together, I'm sure you all agree, an absolutely wonderful conference, which I believe all of you have enjoyed tremendously thus far. Now, as a faculty advisory member to the committee, I'm really proud of them, and at the same time, I'm really embarrassed, Tara and your team members, for having done too little for the conference. So all the credit must go to Tara and her team of very hardworking students. Congratulations once again, Tara, and your team. So thank you. Yes. Thank you for the opportunity for having me chair these sessions on applications. Now, if buying a property in Singapore is all about locations, and locations, I think doing science in Singapore, especially these days, one would agree seems to be about applications, and applications. So this afternoon we're privileged to have two eminent scientists, Dr. Christopher Asplund from Duke-NUS Graduate Medical School and Dr. Guan Cuntai from I2R to tell us respectively about our cognitive limitation and check this out, how we could use our brain to control machines, including playing computer games. I'm sure the students will like it. Now let me say a few words about Chris. Chris is a recent addition to Singapore. Welcome to Singapore. You should visit our casino and contribute to our economy. He joined Yale-NUS some 2 years ago as a senior research fellow working in the cognitive neuroscience lab with Mike Chi. So prior to that, Chris graduated with a PhD, surprise, surprise, in cognitive neuroscience from Vanderbilt University. Later on this year, this autumn, Chris will take on an assistant professorship at the Yale-NUS College. So we wish him the best, and I look forward to welcome Chris as a colleague at NUS. So I've read through the abstract of Chris's talk, and I really look forward to it. You know, it fascinates me. You know how my daughter and the teens here, they could do multitasking like nothing. She'll be on Twitter, on Facebook, on MSN, on iPhone, all at once, and on top of that, doing her homework. Can you believe that? I mean, I, for one, am hoping that you could tell me how to fix my brain, because I can only do one task at a time. So please join me, ladies and gentlemen, to welcome Chris to deliver his talk. Chris.
All right, so first of all, thank you very much for the introduction. Thank you for the invitation to speak here. And thank all of you for coming after lunch to hear what I hope will be a very nice session for you. First, let me say that I'm not going to talk too much about multitasking, unfortunately, now that we've had this nice introduction to it. But let me just say, as a word of caution, that people who think they're very good at multitasking objectively usually aren't that great at it. So don't feel too bad. If you feel you're better at being a single tasker, most of us actually function better in that way, even though most of us don't choose to function in that way. Okay, so cognitive limitations. We've talked a lot about how amazing the brain is, right? You all have amazing brains. They do amazing things. You can remember a lifetime of experiences. You can recognize hundreds of thousands, maybe not hundreds of thousands, tens of thousands of faces. You can perceive objects. You can speak. You can understand all of these great things that the brain does. But it also has some severe limitations to it. So before we get to the limitations, let me build your confidence a bit with a quick demonstration. If I can get this to work. There we go. There's your brain. And let's make it do something. Okay, so what I'm going to show you is I'm going to show you 3 pictures in succession. This isn't the thing. This is just stare at the cross for now. Show you 3 quick pictures in succession. Just tell me what they are at the end. What'd you see? Durian? Yes, we saw Minister of Education. He's here 2 days. And it was Paris at night. You saw a night scene, though. Okay, so you did a lot. Those are up there for less than a second, and you could figure out what they were. You probably remember some of the characteristics of each of those scenes. You did a lot. You perceived a lot of things going on. Now, in this one, this is a scene that's no more complex than those, but there's something changing in the scene. If you see it, don't shout it out. It ruins it for everyone else. But look at the scene. Try to see if you can notice what's changing. I promise it's only one thing. Took you a minute. It's really obvious, right? Okay, most of you see it now. Does everyone see it? Who doesn't see it? All right, keep looking. Keep looking. I'll keep yammering. All right, so the point is, like, it's a pretty big change once you see it, right? There we go. There we go. Now people are seeing it. And there's an aha moment. And once you see it, you can't unsee it again. It's obvious. It was there the whole time. But it took you a while to get to that point. This is what I mean when I say there are limitations to what we can do as well. This is a pretty obvious one. Now that's not the one I'm actually going to talk about mostly today. I'm going to talk about a different limitation. This is actually taking off from what Brian Scholl was talking about yesterday. This is a different type of limitation. In this case, what I'm going to ask you to do is just look for a digit. It's going to be presented amongst a stream of letters. All you have to do is look for the digit and identify it. What'd you see? 2. Okay, very good. Let's try it one more time, just for those who are still learning. 4, very good. All right, one more time. What'd you see? What face? It's not my face. There's another cognitive limitation. Goodness, it's Brian Scholl's face. Brian Scholl once again has caused you not to see something. All right. Let's try it again. Could you see a digit? Okay, what'd you see? 3. Okay, some of you saw it. Let's try one more time for those who are... 2. Everyone saw it that time. Okay, very short-lived. What we just did there, that is a demonstration of an effect we call surprise-induced blindness. And what it was is that there was this unexpected face that disrupted your ability to detect the digit. There was a 7 in the first one that you didn't see. We did a very similar task to this with lots of different people. In this case, we were having them detect an X, just saying whether it was present or not. And it happened about 1/3 of a second before our crucial stimulus, the face in this case. Now, I should say there's nothing special about faces here. I like them because they're amusing. But we've done this with a stream of faces, and the interrupting thing is a letter. Letters aren't particularly exciting, but they do a pretty good job of surprising people if they're expecting faces. So what do we see behaviorally with this kind of thing? So first of all, let me say that most of the trials that we have in these kinds of experiments are like the first 2 that you saw, where it's just the digit, or in this case, just the letter X. There's no face to disrupt you. In that case, people do very well throughout the entire experiments. They can detect that in most trials. But you can see the first couple of these, what we call surprise trials, people are quite impaired at actually detecting that item, just like you were. And as I say, we call this, as you can no surprise, given the time I've said surprise-induced blindness. And one thing we did with this, we've explored this behaviorally. There are a lot of different, very interesting aspects about it. So for example, you saw it's very short-lived, only lives for about 3 trials. It's also short-lived in terms of how long it can disrupt. So if you put that letter or the digit about 1 second after the disrupting stimulus, the face, it doesn't have any effect anymore. Another interesting thing is even if you tell people that there's going to be a face, they still pay attention to that face, and they still miss the digit. Even if you just tell them, no, really, pay attention to the digit. You won't do it. And finally, the last thing I said is it's actually robust across lots of stimulus categories. So what we did with this is we put this task into the scanner, Not all of our subjects look like this. This happens to be my brother, though, so he does look like that. As you heard yesterday, this is an fMRI machine. What it's doing is it's detecting changes in changes in the oxygenation levels in the brain, and we can infer from that there's neural activity that is increasing or decreasing in different parts of the brain when people are doing a given task or when there's a certain event that's occurring. In this case, we're really interested, obviously, in what happens with that surprising event. So what does happen with that surprising event? This is an image of the brain. This is cut axially, so it's cutting your brain like a hamburger bun. And you can see that there are some areas here that are more active during a surprise trial, so when there is that face, than a normal trial. Now, none of these areas are specific to faces, I should say. Those areas tend to be more kind of lower down in the brain. But what these areas are sensitive to is whether that face actually disrupted your behavior. So what you can see here, these are plots of the blood flow changes. And remember that they take some time to unfold. So it takes about 6 to 8 seconds after that surprising stimulus for it to really show up clearly on the blood flow. What you can see is that for the first 2 surprise stimuli, you get more activity in all 4 of these regions than the later pairs. And remember that the first 2 are, on average, those are the ones that were actually disrupting your ability to perceive, in the case of this experiment, the X. And this is just plotted a different way. This is it's an inflated brain or a boxing glove brain. All it is you just take the brain and essentially it's like blowing up like a balloon. It just makes it a lot easier to see what's going on inside some of the deep kind of chasms of the brain. And what you can see here is, first of all, in blue and also this kind of mustard color here, that's what you saw before. Those are the areas that are responding to that surprise stimulus. The areas in red are those areas that are actually involved in just doing the task. So just paying attention to that rapid stream of items that are going by. And what do you have to do in that? You have to search for an item. Once you see it, you have to remember it. And then after the trial is over, you actually have to make a response as to, yes, I saw it, or no, I didn't. So all of those are contributing to activity in these other regions. And what you can see in the ketchup-colored thing, in the mustard-colored area, that's actually the overlap between those 2. Now, what's interesting about this is that if you think about what is going on in this case, the surprising stimulus is disrupting your task, right? This is the surprise stimulus kind of activity, and this is the activity of doing the task. So you know they have to interact somewhere. And this figure here actually shows one possible way in which or one possible place in which they could be interacting, this region right here. Now, behaviorally, it makes sense that they have to interact as well, that you have this interaction between what you're doing, what your kind of your goal, and what is happening in your environment. And there's a constant interplay between these 2 kind of forces on your behavior. That brings me to the first kind of take-home message here, is that we face cognitive trade-offs. In this case, the relevant trade-off is between staying on task and investigating something new. Now, one example of this is if you're, say, very engrossed in playing Angry Birds on the MRT, you might miss your station. I've never done that before, I assure you. Alternatively, if you're playing Angry Birds and a child screams, again, on the MRT, that hasn't happened to me either, you might be disrupted from that task you're doing. So there's a trade-off in that you cannot necessarily do all of these things at once. You might not be able to concentrate very heavily on killing pigs. At the same time, you're trying to listen for your stop. Second point I want to make is that novelty is powerful. We've seen this kind of, I actually saw this earlier with Prof. Singh's talk.